Good morning, students. Welcome to Good Samaritan School online classes. In the last class, we discussed on the force on current carrying conductor in a magnetic field. It means if you keep any current carrying conductor like this, A and B, an aluminum rod, which is kept in between the magnetic field, the horseshoe magnet, it experience some force based on the same thing. That means if it kept perpendicular to the magnetic field, then it experienced some force. Based on that, we have learned Fleming's left hand rule, and also we learned electric motors. Okay, these topics are very important, and also we learned how the electric motor works, right? And also what are the uses of these electric motors in our day-to-day life activities. And today we are going to learn a new topic called electromagnetic induction. As we know that in the starting of the class itself, we discussed always the electricity and magnetism, or electricity and magnetic, they both are interrelated to each other. I just want to show it in your, it's in your book, page number 223. Here we have learned that electricity and magnetism are linked to each other. That means they both are linked with each other. So based on this concept only, we are learning all these things, and now we are going to learn on electromagnetic induction. What is electromagnetic induction? As we learned or studied that when a current carrying conductor is placed in a magnetic field such that the direction of the current is perpendicular to the magnetic field, it experiences a force like this, what we learned. Okay, when a current carrying conductor is kept in between the magnetic field perpendicular to each other, then it experiences some force. Okay, it moves. So this force causes the conductor to move, right? This is what we learned. But now let us imagine, okay, a situation that in which conductor is moving inside the magnetic field. Okay, for example, this is the conductor and this is the magnetic field. Okay, when it moves inside the magnetic field, does it produce any electricity, current? What happens? Okay, that is what we are going to learn in this. This was first studied by the English physicist whose name is Michael Faraday, and Michael Faraday is one of the greatest scientists of physics. And based on his discovery only, there are lots of generators are created. Okay, that is what we are going to learn in this topic. Take an example and an activity 13.8 which is given in your book. Okay, let's learn about this activity. What is that activity talks about? Take a coil of a wire AB. Okay, before that we learn what is electromagnetic induction. The electromagnetic induction is nothing but the phenomenon of production of electromotive force. Electromotive force is nothing but EMF. EMF is nothing but, you think in the other way, current. Okay, electricity. The phenomenon of production of current across the conductor when placed in a changing magnetic field is called electromagnetic induction. So what it talks about, let's take an example. This activity, we have taken AB, a rod, or we can take it as an any cardboard or roll of paper. In that we round the we take several turns of a coil, copper coils over there, and connected with a galvanometer. What is galvanometer and why it is used? It is used to find whether this area is having current or not. Okay, that is how we are, that is for the reason we are using galvanometer. It is given in your book also. You can look at here, page number 234. A galvanometer is an instrument that can detect the presence of current in a circuit. अगर ये सर्क्यूट में करंट है और नहीं है तो उसको फाइंड आउट करने के लिए ये गैल्वेनोमीटर यूज़ करता है. Okay, take an example. We have taken a bar magnet facing north pole towards a B. So this is normally they are not connected with any battery, nothing. Just a coil connected with galvanometer. Why this galvanometer is connected? Just to identify whether the current is flowing in this coil or not. That's it. So when this bar magnet is going taking towards this B, or you can keep it goes towards this inside लेके जाओ. So what you find, you can see the galvanometer showing some deflection. पहले zero में था, zero is at the middle, and it shows the direction like this, and it means there is a current is passing. Okay, what they are doing, after take it inside, they are keeping the magnet here itself, अंदर ही रख दिया. Then what happened? Immediately, पहले ऐसे था, अंदर लेके जाएंगे तो ऐसे हो गया. When we keep it inside that, then it will come back to zero. That means no current is flowing. Now what happened? I'm going to pull it up outside. बाहर निकाल रहा है. बाहर निकालने के time, then it moves towards opposite direction. Can you understand? If it moves inside, then it shows like this. When we keeping it in the inside itself, then it will be like that. Zero में आ गया. Then we are taking it outside, then opposite में जा रहा है. So this makes everyone surprised. Why it happens? It happens, you can check, and you can also check that if you have moved south pole of the magnet towards the end B, the coil, the deflection of the galvanometer would just be opposite of the previous case. That means B के साइड से साउथ पोल ऐसे लेके जा रहा है. पहले नॉर्थ पोल लेके गया था, and now we are taking south pole in that, so it moves towards opposite direction. When the coil and the magnet are both stationary, keep it as such, then there is no deflection on the galvanometer. It is thus clear from this activity, what we are learning from this activity, that motion of the magnet with respect to the coil produce an induced potential difference only by the movement, okay, inside and outside. If you keep it inside ऐसे रख दिया तो कोई current नहीं pass करेंगे. But when we take it inside and taking it outside, the movement of this magnet represents to this coil, then only I can find there is a current is coming out, which sets up a induced current in a circuit. Okay, there is a short summary of Michael Faraday is given here in the box. Please go through this and read, and you will get more inspired of his of his life, because he's normally a book binding person. He was working in a book binding shop in early days, and after that inspired with some lectures, and then he got a big breakthrough. So it gives you an inspiration how he became a scientist. Okay, there is another activity here, activity 13.9, which is given in your book at page number 235. You go through that also. What is here it talks about, we have taken two coils. Coil 1, okay, say for example you see more than 50 to 100 turns of coil there, and this is connected to a battery, positive to negative. So what happened, the current will flow in this. But here little bit थोड़ा सा डिस्टेंस देके यहाँ पे another coil make another 50 to 60 rounds, and this is connected toward galvanometer, but there is no connection between this and that, nothing. But here what we are going to learn from this activity, when the current is passing through in this coil 1, you find there is a deflection takes place on this coil galvanometer. Why it is happening? So we observe that soon the current in the coil 1 reaches either a steady value or 0. The galvanometer in coil 2 shows no deflection. अगर एक current pass नहीं करेंगे तो इसमें कोई deflection नहीं है. From these observation, what we are concluding from that is the potential difference induced in coil 2. There is some movement takes place in coil 2 whenever the electric current through the coil 1 is changing. अगर यहाँ पे करंट लेस हो रहा है, कम हो रहा है, नहीं तो ज़्यादा हो रहा है, तो then only I find there is a deflection takes place on the coil 2. Correct? If there is no current is flowing here and there is no deflection here, So we can say that coil 1 is called the primary and coil 2 is called the secondary. So unless there is no change in primary, there is no change of deflection in secondary galvanometer. This is a very important point you should understand. Thus the magnetic field lines around the secondary coil also changes. Hence, the change in magnetic lines associated with the secondary coil is the cause of induced electric current in it. So main thing is what? The change in the magnetic field lines associated with the secondary coil is the cause of induced current in it. यहाँ से current induce होके यहाँ से current induce होके इसको induce कर रहे हैं because of the current flow हो रहा है तो यहाँ पे क्या हो जाएगा magnetic field हो जाएगा यहाँ पे magnetic field हो रहा है तो यहाँ से इसको induce करके then there is a current will be flowing from here. Okay, this is what happening. So from this process by which the change of magnetic field in a conductor induces the current in another conductor is called electromagnetic induction. So what we are learning, the changing of magnetic field, यहाँ पे current pass करेंगे तो change of magnetic field हो रहा है in the conductor and induces the current in the another conductor is called magnetic induction, right? So in practice, we can induce current in a coil either by moving it in a magnetic field or by changing the magnetic field around it. It is a convenient in most situations to move the coil in a magnetic field. Okay, based on this, we are going to learn another rule called Fleming's right hand rule. Fleming's right hand thumb rule, you can move like this, okay? Stretch your thumb, forefinger and the middle finger just perpendicular to each other, and the thumb talks about the motion force, and this forefinger again talks about the electric field, magnetic field, and this is an induced current. So what we are learning here, the motion takes place, okay, movement and in a magnetic field, and this induces the current. Okay, here there is a small word change here. We are not simply using current, it is induced current. Current was induced when there is a motion takes place in the field, magnetic field. That's what here is given. An induced current is found to be the highest when the direction of the motion of the coil is at right angles to the magnetic field. A current कब induce होगा? कब होगा? The induced current is found to be highest कब? When the direction of the motion of the coil is at the right angles to the magnetic field. Magnetic field ऐसे हो जा रहे तो the if the motion or the coil the direction, the induced current is found to be highest in the direction of the motion of the coil is at the right angle to the magnetic field. The motion, if it is right angles to that, then definitely you can see the current will be induced. Current आ जाता है. Okay, so to understand this, stretch your thumb, forefinger and middle finger of your right hand perpendicular to each other. The forefinger indicates the direction of the magnetic field. Thumb shows the direction of the motion of the conductor. The middle finger shows the direction of induced current. Okay, this simple rule is called Fleming's right hand rule, right? So based on this only, electric generators are going to be formed, and then but this topic is not actually in your syllabus. Electric generators, domestic currents and AC and DC currents are not in our syllabus, but this is the end of our syllabus up to Fleming's right hand rule. Okay students, if you have any doubt on this topic we have learned today, electromagnetic induction and Fleming's right hand rule, please do ask me in my WhatsApp number. Thank you student and have a nice day.